Hello everyone, welcome back. In this video, we're going to look at some of the applications of the derivative. Now, in the previous videos, we were looking at ways of calculating the derivatives of certain functions, as well as the method of implicit differentiation. So now we can look at where the derivatives can be used to solve certain real-world problems. Now, back in chapter 2, we studied the slope of the secant line as well as the tangent line to a curve at a point. So now let's return to these definitions, but also give a different interpretation of what these mean. So if we're given a function y equals f of x, and we have 2 points with coordinates x1, comma f of x1, and x2, comma f of x2, then we can define what is called the difference quotient as follows. So we have delta y over delta x, which is the difference in the y coordinates of these 2 points divided by the difference between their x coordinates. So delta x is x2 minus x1, and it represents the change in x, and delta y is f of x2 minus f of x1, where it corresponds to the change in y. And this difference quotient is called the average rate of change of y with respect to x over the interval from x1 and x2. So it gives us an average rate of change for the function on this interval. Now if we take the limit where delta x goes to 0, then we obtain the derivative f prime at x1. And so this is called the instantaneous rate of change of y with respect to x. And so we can also write this using Leibniz notation. So dy over dx is the limit as delta x goes to 0 of the difference quotient, and it's given by this limit. So let's have a look at what this means geometrically. So the average rate of change and the instantaneous rate of change corresponds to the slope of the secant line and the slope of the tangent line, respectively. So over on the left, we have a function y equals f of x and the 2 points p and q. And so the average rate of change, which is the change in y divided by the change of x, is really just the slope of the secant line through these 2 points. So it tells us how much on average the function will change over the interval from x1 to x2. Now over on the right, we have the derivative at x1, which is going to be the slope of the tangent line at this point. And it represents the instantaneous rate of change at x1. So it tells us how much the function will change at this particular point. So now let's have a look at a physics application of the derivative. So suppose that we have a particle which moves in a straight line, and we'll let the function s be a function of t, represent the position of the particle at a given time t, then delta s over delta t, so that's the change in position over the change in time, will represent the average velocity over the time period delta t, and v of t is going to be the derivative ds over dt, which will represent the instantaneous velocity, which is the rate of change of displacement with respect to time. So we're given that the derivative of the position function gives us velocity. And the instantaneous rate of change of the velocity function with respect to time is called the acceleration. And so the acceleration, a of t, is the derivative of the velocity function. And it's also the second derivative of the position function, or sometimes called the displacement function. Now let's suppose that the position of a particle is given by the equation s equals f of t, which is given by t cubed minus 6t squared plus 9t, where t is measured in seconds and s is measured in meters. So let's find the velocity at time t. So the velocity function v of t is the derivative of displacement function. And so we need to differentiate s with respect to t. And we are given that s is equal to t cubed minus 6t squared plus 9t. So we use the power rule to differentiate the function. The velocity is given by 3t squared minus 12t plus 9. So this is the velocity function at time t. So what is the velocity after 2 seconds and after 4 seconds? So now we can use the velocity function to determine the velocity of the particle at these times. So if we want to find the velocity at 2 seconds, then we substitute 2 into the velocity function. So the velocity is going to be 3 times t squared minus 12 times 2 plus 9. So that gives us 3 times 4 minus 24 plus 9. That is 12 minus 24 plus 9. So we have negative 12 plus 9, which is negative 3. Now the velocity will have units in meters per second. Okay, so the position is measured in meters and time is measured in seconds. And so the velocity is at negative 3 meters per second. Now after 4 seconds, we have 3 times 4 squared minus 12 times 4 plus 9, which is 3 times 16 minus 48 plus 9. So that is 48 minus 48 plus 9. That gives us positive 9 meters per second. Now, when is the particle at rest? Well, the particle is at rest if the velocity is equal to 0. And so our velocity function is 3t squared minus 12t plus 9. And so if we set the velocity function equal to 0 and then solve for the times t, then these are the times where the particle will be at rest. So let's set this equal to 0 and then solve for t. So what we have is a quadratic. And so let's see if we can simplify our equation. We notice that there's a common factor of 3 out of all terms. So if we factor out a 3, we're left with t squared minus 4t plus 3 is equal to 0. Now t squared minus 4t plus 3 is factorable, and they factor to t minus 3 times t minus 1. And so now we can set each factor equal to 0 and then solve for t. So we have t minus 3 is equal to 0, or t minus 1 equals 0. So that tells us that t is equal to 3 seconds, or t is equal to 1 second. So these are the times when the particle is at rest. Now, when is the particle moving forward? That is, in the positive direction. Well, the particle is moving forward if the velocity is greater than 0, or in other words, where it's positive. And so what we want to do is solve the inequality where the velocity function is equal to 0. And so our velocity function, after factoring, is 3 times t minus 3 times t minus 1. And so we want to solve for when this function is positive. So here we can use a number line to help us determine the times where the velocity function is positive. So on the real number line, we're going to plot the times when the velocity is equal to 0, or when the velocity is at rest, or when the particle is at rest. So back in part C, we determined these times were at 1 and 3. So now what we'll do is test each interval for the sign of the velocity function. So what we have are 3 intervals. So from negative infinity to positive 1, from positive 1 to positive 3, and from 3 to positive infinity. So what we'll do is choose a value of t within each of these intervals, and then test for what the sign of the velocity function is. So for example, if we're testing between negative infinity and positive 1, we can choose t to be 0. So if we substitute 0 into the velocity function, what we'll get is 3 times 0 minus 3 times 0 minus 1. And this will give us positive 9. Now the value of the velocity function we're not really concerned with. All that we care about is whether it's positive or negative. So we're given that the velocity is positive on this interval, which means that the velocity is, or the particle is moving forward within this interval. So now let's test a value between 1 and 3. So for example, we can test positive 2. So if we substitute 2 into this function, we get 3 times 2 minus 3 times 2 minus 1, and we get negative 3. And so the velocity will be negative between the times 1 and 3. And lastly, let's test a value between 3 and infinity. So for example, we can choose 4. And if we substitute this into our velocity function, we get 3 times 4 minus 3 times 3 minus 1, which gives us positive 9. So that tells us that the velocity is going to be positive between 3 and infinity. Now we know that the velocity will be 0 at 1 and 3, which is not a positive number, so we will exclude these from our interval. So now we can write down the times for when the velocity is positive or when the particle is moving in the positive direction. Now typically, time is measured from 0, so we don't include negative time in our interval. So the particle is moving forward on the interval from 0 to 1, union 3 to infinity. So now let's draw a diagram that represents the motion of the particle. So we're given that the particle is at rest after 1 second and after 3 seconds. So let's determine the position of the particle when the particle is at rest. So that means we'll evaluate the position function at 1 and at 3. So these were the times where the function or where the particle is at rest. So the position at time 1 is given as 1 cubed minus 6 times 1 squared plus 9 times 1. So that is 1 minus 6 plus 9, which is 4. And the position is measured in meters. And then at time 3, the position of the particle is at 3 cubed minus 6 times 3 squared plus 9 times 3. So that is 27 minus 54 plus 27, which is 0 meters. So the position of the particle after 3 seconds is at 0 meters, or where the particle started. So now let's draw a diagram which will represent the position of the particle. So let's suppose the particle starts at the origin, so at position 0. And we'll also use our intervals of when the particle is moving forward. So after 1 second, we know that the particle has traveled 4 meters. And we know that the particle moves forward between 0 and 1. So the particle starts from the origin and then travels 4 meters in the positive direction. So this happens when time is equal to 1 second. Then we know that between 1 second and 3 seconds, the particle is moving in the reverse direction. And at 3 seconds, the particle is back at the origin. So between 1 second and 3 seconds, the particle has moved back in the reverse direction and is back at the origin after 3 seconds. And then the particle is moving in the forward direction from 3 seconds to infinity. And so after 3 seconds, the particle will move in the forward direction for all of time. And so this is the motion of the particle. So it moves forward for 1 second, it moves backwards for 2 seconds, and then it moves forward after 3 seconds. So now let's find the acceleration at time t. So the acceleration function is the derivative of the velocity function, or the second derivative of the displacement function. So let's differentiate the velocity function. We know that v of t was 3t squared minus 12t plus 9. And so taking another derivative, we have 6t minus 12. Now what is the acceleration after 4 seconds? Well, we can substitute 4 into the acceleration function. We have 6 times 4 minus 12. That's 24 minus 12, or 12. And the units for acceleration is in meters per second squared. Now, when is the particle speeding up and when is the particle slowing down? Well, the particle is speeding up when both velocity and acceleration functions are the same sign. So either they're both positive or both negative. And the particle is slowing down when the acceleration and velocity function are opposite signs. So let's have a look at when the acceleration function is positive and negative. So what we'll first do is solve for when the acceleration function is 0. So that happens when 6t minus 12 equals 0. And solving for t, we end up with t equals 2. And so now we'll test on a numbered line for when the acceleration is positive or negative. And so like what we did for the velocity function, we will plot when the acceleration function is 0 on the numbered line. So that happens when t is 2. And we typically start time from 0, and we don't start from a negative time. So we'll plot 0 as well. So now let's test within these two intervals for when the acceleration is positive and negative. So between 0 and 2, so let's suppose we'll let t be 1, the acceleration function is going to be 6 times 1 minus 12. That is 6 minus 12, which is negative 6. So we know that the acceleration is going to be negative from 0 to 2. And now let's test when the acceleration, when the time is between 2 and infinity. So for example, let's test 3. And substituting this into the acceleration, we get 6 times 3 minus 12. That's 18 minus 12, which is positive 6. So we know that the acceleration is positive on this interval. So now we'll plot both the velocity and acceleration intervals next to each other so that we can compare when they have the same signs or when they have opposite signs. So we know that for the velocity function, it was 0 at 1 and 3, and it was positive between 0 and 1, it was negative between 1 and 3, and then it's positive from 3 to infinity. Now for the acceleration function, we determined that between 0 and 2, the acceleration is negative, and between 2 and infinity, the acceleration was positive. So I'm going to mark in blue for the times when they have opposite signs. So between 0 and 1, the velocity function is positive, but the acceleration function is negative. So between 0 and 1, they have opposite signs. And between 2 and 3, the velocity function is negative, and the acceleration function is positive. So that is when they have opposite signs. They have the same sign if time is between 1 and 2 seconds, or from 3 to infinity. So that tells us that the particle is speeding up from the interval from 1 to 2, union 3 to infinity. And the particle is slowing down on the interval from 0 to 1, union 2 to 3. So let's suppose that a balloon is being pumped with air, and both the volume and the radius of the balloon are changing over time. So over time, both the radius and the volume is going to be increasing over time. Now the rates at which these two quantities are increasing are related to one another. And if we happen to know one of these rates, such as how fast the volume is increasing, then we can determine how fast the other quantity is changing. Now these types of problems are called related rates, and the general procedure to solving these types of problems is to find an equation that relates the two quantities that are changing and then use implicit differentiation with respect to time. Now the resulting equation will give us the relationship between the rates of change. And here I've listed the steps to solving the related rates problems, and we'll go through these steps as we look at the different examples. So in the first example, we have a spherical balloon that is being pumped with air so that its volume is increasing at 100 centimeters cubed per second. How fast is the radius increasing when the radius is 5 centimeters? So let's draw our diagram, and I typically like to use two different diagrams. One is called a general picture of our situation. So we see that the volume and the radius are both increasing over time. And the other diagram will provide us the instantaneous moment that we're interested in. And what we're interested in is how fast the radius is increasing the moment when the radius is 5 centimeters. And so when the radius is at 5 centimeters, we want to know how fast the radius is increasing. So now let's determine the quantities that are known and unknown. So what are we given from the problem? Well, we're given that the volume is increasing at a rate of 100 centimeters cubed per second. Now we can write the rate at which the volume is increasing by using our derivative. So if V represents the volume of the balloon, then the rate of change of the volume is dV over dt. So the change in volume over the change in time. And we're given that the volume is increasing at 100 centimeters cubed per second. And I would like to emphasize that this is a positive rate, meaning that the volume is increasing. Now, what are we trying to find? What we want to know is how fast the radius is increasing when the radius is 5 centimeters. And we can represent this rate as a derivative. So if r represents the radius of the balloon, then that tells us that dr over dt is what we're looking for when the radius is 5 centimeters. So now the next step is to write an equation that relates the two variables that we're interested in. So one is the volume of a balloon, and the other is the radius. So what is the relationship between the volume of the balloon and the radius of the balloon? Well, we know that the volume of a sphere is given as V is equal to 4/3 pi r cubed. So this is the relationship between our two variables. So we can calculate the volume of the balloon by using this formula given its radius. So we want to differentiate both sides of the equation with respect to t. And the key thing to remember about implicit differentiation is to remember the chain rule. So the derivative of v with respect to t, that is dv over dt. Now on the right-hand side, we have the derivative of 4/3 pi r cubed. And so here we need to use the power rule and also remember to use the chain rule. So the 4/3 pi is a constant, so that stays in front. We multiply the 3, so that gives us 4/3 pi times 3r squared. And then remembering the chain rule, we multiply this by dr over dt. So now let's simplify. We have dv over dt equals, now the 3's can cancel, and we're left with 4 pi r squared times dr over dt. And so now what we have is the relationship between our two rates of change. So we're given that the rate of change of volume with respect to time is 4 pi r squared times the rate of change of the radius over time. So now we can solve for dr over dt by dividing both sides by pi r squared, 4 pi r squared. So now we can substitute our given quantities to determine dr over dt when the radius is 5 centimeters. So that's 1 over 4 pi times 5 squared multiplied by dv over dt, which is 100. And this will simplify to 100 over 4 times 25, which is 100 pi. And this can be simplified to 1 over pi. Now the radius is measured in centimeters and time is measured in seconds. So as a rate, this is centimeters per second. Now note that dr over dt is positive, meaning that the radius is increasing at 1 over pi centimeters per second. So the radius is increasing at 1 over pi centimeters per second when the radius is 5 centimeters. In the next example, we have an oil spill that spreads in a circular pattern. And if the radius of the spill is increasing at 2 meters per second, how fast is the area of the spill increasing when its diameter is 120 meters? So let's first draw a diagram of our situation. So we have an oil spill. And it spreads in a circular pattern. So over time, the spill is getting larger. And what we're interested in is how fast the area of the spell is increasing when its diameter is 120 meters. So we'll let A be the area of the oil spill. R is going to be the radius of the spill, and we'll let D be the diameter. So now let's write down what we're given. So we know that the radius of the spill is increasing at 2 meters per second. So as a derivative, this can be represented as dr over dt. And we're given that is increasing at 2 meters per second. And what we want to look for is how fast the area of the spill is changing when the diameter is 120 meters. So as a derivative, that is dA over dt when the diameter is 120 meters. So now the next step is to relate the two variables. So how can we relate the area of the spill with the radius of the spill? Well, we know that the area of the circle is given as pi r squared. So there's our relationship between the area and the radius of the spill. Now the next step is to differentiate both sides of the equation with respect to t. So the derivative of a with respect to t is equal to the derivative of pi r squared with respect to t. So now we calculate these derivatives. Remember that we have chain rule. So the derivative of pi r squared is 2 pi times r times dr over dt. So now we can use the given quantities to determine how fast the area of the spill is increasing the moment when the diameter is 120 meters. Now if we have a look at our equation, what we have is r and not the diameter, but we know that the diameter is 2 times the radius. And so that tells us that the radius of the spill when the diameter is 120 meters is 60 meters. And so now we can substitute these values to determine how fast the area is changing. So that's 2 pi times 60. And the radius of the spill is increasing at 2 meters per second. And so simplifying, this tells us that the area of the spill is increasing at 240 pi meters squared per second. So the area of the spill is increasing at 240 pi meters squared per second when the diameter is 120 meters. In the next example, we have a ladder that is 10 feet long and it rests along a vertical wall. So suppose the bottom of the ladder slides away from the wall at a rate of 1 feet per second. So in part A, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So let's have a look at drawing the diagrams of our situation. So in general, we have a vertical wall and the ladder, which rests along the wall, which is 10 feet long. So over time, the top of the ladder will slide down the wall, and it will also move away from the wall. So let's call the horizontal distance x and the vertical distance y. So what we're interested in is how fast the top of the ladder is sliding down the wall when the bottom of the ladder is 6 feet from the wall. So the moment when x is 6 feet, we are interested in determining how fast the top of the ladder is sliding down the wall. So let's write down the given quantities. So we know that the bottom of the ladder is sliding away from the wall at 1 feet per second. So as a derivative, that is dx over dt, and we're given that it's sliding at 1 feet per second. Now what we're looking for is how fast the top of the ladder is sliding down the wall. So as a rate, that is dy over dt when x is 6 feet. So now let's write an equation that relates our given quantities in the left picture. So what we have is a right angle triangle, and we can relate the sides of the right angle triangle by using Pythagorean's theorem. So we have that x squared plus y squared is equal to 10 squared. And now that we have an equation that relates our two quantities, we can now use implicit differentiation on both sides. So taking derivative of both sides with respect to t, we have that the derivative of x squared with respect to t plus the derivative of y squared with respect to t plus the derivative of, or it's equal to the derivative of 100. So here we need to remember to use the chain rule. So we have 2x times dx over dt plus 2y times dy over dt is equal to 0. So now that we have the equation involving the rates, we can now determine dy over dt. However, if we look at this equation, we're given x, which is 6 feet. We have dx over dt. We're given, or we're looking for dy over dt, but we don't know what the y value is. And so let's have a look back at our instantaneous picture. Okay, so we can solve for y in this triangle by using Pythagorean's theorem. So the moment when x is 6 feet, Pythagorean theorem says that y squared plus 6 squared is equal to 10 squared. So y squared is 100 minus 36. Y squared is 64. So y is plus or minus root 64, which is plus or minus 8. Now, since distances can't be negative, we will choose the positive root. So y is going to be 8 feet. So now we can go back and substitute these values into our resulting equation, and then we can solve for dy over dt. So we have 2 times 6 times 1 plus 2 times 8 times dy over dt is equal to 0. So that gives us 12 plus 16 dy over dt is equal to 0. So 16 dy over dt is negative 12. So that tells us that dy over dt is negative 12 over 16, or it's negative 3 over 4. So distances are measured in feet, and time is measured in seconds. So dy over dt is negative 3 over 4 feet per second. So since it's a negative quantity, we know that y will be decreasing at this rate. So the top of the ladder is decreasing at 3 over 4 feet per second when the bottom of the ladder is 6 feet from the wall. Now in part B, how fast is the angle between the ladder and the ground changing when the bottom of the ladder is 6 feet from the wall? So again, let's draw our instantaneous and general picture. So in general, we know that x will be increasing. We'll let theta be the angle between the ground and the ladder. And we're interested in knowing how fast the angle between the ladder and the ground is changing when the bottom of the ladder is 6 feet from the wall. So we're given that the ladder is moving away from the wall at 1 feet per second. And what we're looking for is how fast the angle is changing when x is 6 feet from the wall. So the first thing is to write down an equation that relates our quantities in our general picture. So we have the angle theta, we have the sines x and 10 in our right triangle. So which trig ratio will relate these quantities together? So we have the adjacent side and the hypotenuse. Well, we know that cosine is the adjacent side over the hypotenuse side. So cosine of theta is x divided by 10. So there is the equation that relates our quantities. So now we can use implicit differentiation to find an equation that relates the rates. So the derivative of cos with respect to t is equal to the derivative of x over 10 with respect to t. So again, we need to remember to use chain rule. The derivative of cos is negative sine. Then we multiply by d theta over dt. And the derivative of x over 10 is 1 over 10 times dx over dt. So now if we have a look at this equation, we have dx over dt. We're looking for d theta over dt, but we don't know the sine of theta. So this is where we go back to our instantaneous picture so that we can determine the sine of theta. So the sine of theta is equal to the opposite side over the adjacent side. Now back in part A, we determined from Pythagorean's theorem that this side was 8 feet. And so we can determine the sine of theta, which is the opposite side over hypotenuse. So the sine of theta is going to be 8 over 10. So we have negative 8 over 10 times d theta over dt is equal to 1 over 10 times 1. So solving for d theta over dt, we have negative 1 over 8. And whenever we are measuring angles, the convention is that we use radians as our measurements. So the units for d theta over dt is in radians per second. So the angle is decreasing at 1 over 8 radians per second. when the bottom of the ladder is 6 feet from the wall. Now in the next example, we have water that drains through an inverted conical filter at 2 cubic centimeters per minute. If the filter has a height of 16 centimeters and a radius of 40 millimeters, then how fast is the water level changing when the water is 8 centimeters deep? So the first thing we'll do is draw a picture of our situation. So we have a conical filter, and water is being drained from the filter. Now the filter has a height of 16 centimeters, and its radius is 40 millimeters. So we're going to let R be the radius of the water level and H be the height of the water level. And we'll also let V be the volume of the water in the filter. So we want to know how fast the water level is changing when the water is 8 centimeters deep. So our instantaneous picture is when the height is 8 centimeters. So let's write down the quantities that were given. So we are given that water is being drained at 2 cubic centimeters per minute. So the volume of the water is changing, and in particular, it is decreasing. So it would be negative 2 centimeters cubed per minute. Now what we're looking for is how fast the water level is changing when the water is 8 centimeters deep. So as a derivative, that is dH over dt when h is 8 centimeters. So now what we're looking for is a relationship between the volume of the water to the height of the water. So we know that the volume of a cone is 1/3 pi r squared times h. However, if we look at this equation, there are too many variables. We have v, r, and h, and because we are looking for dh over dt, we need to eliminate the r variable. So now let's have a look at our diagram, our general picture. So we can find some sort of relationship between the radius of the water level and the height of the water level. So if you stare at this diagram long enough, you may notice that there are two similar triangles. So we have one triangle here, and there is a larger triangle from the cone. So let's draw these out so we can see what relationship we have between these two variables. So we have the larger triangle, which is from the cone. So its radius is 40 millimeters. So let's just convert this to centimeters. So 40 millimeters will be 4 centimeters, so that we're working with the same units. And the height of this cone is 16 centimeters. Now from the water, we have another triangle, and it has a radius of r and a height of h. So now we can use similar triangles to relate the ratios together. So similar triangles says that the ratio of the sides are equal. So if we look at the smaller triangle, the ratio of that side, r, over the larger triangle, which is 4 centimeters, is the same as the ratio of the other sides, which is h over 16. So the ratio of the sides are equal. So we have a relation between the radius of the water level as well as the height of the water level. So if you were to solve for r in this equation, we multiply both sides by 4, we get r is equal to h over 4. And now we can substitute this into our volume equation so that we eliminate the r variable. So the volume is going to be 1/3 times pi h over 4 squared times h. So now let's simplify our formula. We have 1/3 times pi times h squared over 16 times h, which is pi over 48 times h cubed. So now that we have eliminated the r variable, we can now use implicit differentiation. So we will differentiate both sides with respect to t. So we have dv over dt is equal to pi over 48 times 3h squared. And remember, we use the chain rule and multiply by dH over dt. So simplifying, this is pi over 16 times h squared times dH over dt. So now we can substitute our quantities. We know that dV over dt is -2 is equal to pi over 16. We're interested in the rate when the height is 8 centimeters. So we have 8 squared times dH over dt. So then this gives us -2 is pi over 16 times 64. And then solving for dH over dt, we have -32 is equal to pi times 64 dH over dt. So dH over dt is -32 over 64 pi, which is -1 over 2 pi. Now height is measured in centimeters, and time is measured in seconds. And so dH over dt is -1 over 2 pi centimeters per second. So this tells us that the water level is decreasing at 1 over 2 pi centimeters, and I lied. The units are measured in minutes, so that is centimeters per minute, when the water level is 8 centimeters.